Welcome to the deep dive. Get ready to dig deep with us today because we are plunging into the absolute bedrock of our planet, the fascinating world of geology.
Mm.
We've taken a stack of sources that cover everything from the Earth's fiery beginnings deep inside to the solid ground beneath our feet, the incredible history locked in rocks and fossils, and even how we use cutting-edge technology to study it all.
That's right. And the source material we looked at, it's like a really comprehensive guide. It walks us through the basic ideas, the powerful processes, and the practical applications of geology.
Right.
What's particularly helpful, I think, is the focus on examples and case studies right here in India and Maharashtra.
Yeah, that grounding is useful.
It is.
Yeah.
So our mission with this deep dive is really to pull out the most important nuggets, uncover some, surprising facts, and help you connect the dots so you can feel truly informed about this dynamic planet we all live on.
Okay, so we're going to touch on how Earth actually formed and got its distinct layers, what the different types of rocks tell us about its past.
Yeah, the stories in the stones.
Exactly, and how ancient life left its mark, the immense forces that shape the surface through structures like folds and faults,
All that bending and breaking.
the hidden wealth of resources buried underground, the vital role of groundwater, which is so important,
Critically important.
the powerful and sometimes dangerous geohazards like earthquakes and volcanoes, and finally, how tools like satellites and GIS let us see the unseen.
It's a vast subject, definitely. But we're going to try and break it down for you.
Think of this as your express lane to understanding the foundational concepts of geology, presented in a way that hopefully keeps you hooked. Okay, let's unpack this.
We'll do it.
Let's start by going way back. I'm talking about 4.56 billion years ago. It's just mind-boggling to think about Earth starting its journey as just a small planetesimal. What was happening in those very, very early days to create the planet we know?
Well, it was an incredibly violent and dynamic time. The sources talk about processes like stepwise differentiation, initiation of magma oceans.
Magma oceans, wow.
Yeah, imagine the early Earth as largely molten, just a ball of hot liquid rock. And denser materials, things like iron and nickel, were pulled by gravity inwards, separating out to form the core.
Because they were heavier.
Exactly. Heavier stuff sinks. And the lighter silicate materials rose towards the surface to form the mantle and eventually the crust. This huge process of sorting material by density is why we have the layered Earth structure we see today.
Okay, so this initial sorting created the distinct layers we talk about. The core, the mantle, and the crust. How do those stack up today? What do they look like?
Right at the center, you've got the core. And it's actually split into a solid inner core and a liquid outer core.
Why the difference? Both are incredibly hot, right?
They are. But the sources mention this difference is mainly due to pressure. The pressure is so immense in the very center, it keeps the inner core solid, despite the heat. It's actually the movement of the liquid iron in the outer core that's believed to generate Earth's magnetic field.
That's amazing. And we can't exactly drill down there to check, can we?
Huh? No, not even close. We know about the core mainly through indirect methods, like seismology. Basically, watching how earthquake waves travel through the Earth tells us about the different layers they pass through.
Okay, so we have the core. Then comes the massive mantle.
The mantle is huge, stretches about 2,900 kilometers thick. It's mostly silicate rock, but under intense heat and pressure. Now, while the lower mantle is very viscous, things super thick honey,
Right.
the upper mantle is more fluid, relatively speaking, and it convects.
Convex, like water boiling in a pot.
Sort of, yeah, like
Yeah.
very thick, slow-moving syrup boiling. These convection currents are absolutely crucial because they are the primary engine driving movement in the outermost layers.
Which brings us to the thin, brittle skin we actually live on, the crust.
Right, the crust is part of lithosphere, which is the rigid outer shell.
Huh.
And it's surprisingly thin compared to the other layers, maybe only 5–10 kilometers under the oceans, up to, say, 70 kilometers under continents.
And there are two main types.
Two main types. Oceanic crust, which is thinner, denser, younger, mostly basalt, and continental crust, which is thicker, less dense, and much, much older. It can contain rocks dating back 3.8 billion years, which gives us crucial clues about Earth's deep history. The sources even mention how crust and eroded sediments are eventually recycled back into the Earth over long timescales.
And these layers aren't just smoothly transitioning into each other, are they? I think the sources mentioned boundaries.
Yes, exactly. Geologists identify these boundaries using changes in seismic wave velocities as they travel through the Earth. They're called discontinuities.
Like the moho, I remember that name.
The moho, that's the famous one. It marks the boundary between the crust and the upper mantle. But there are others, like the Ripetti, Gutenberg, and Lehman discontinuities, which delineate deeper boundaries within the mantle and core. They're basically markers of fundamental changes in the Earth's composition or physical state.
So we have this layered structure, mostly silicate compounds, with heat driving movement from deep inside. What does this internal heat engine mean for us up here on the surface?
It means everything. It means the Earth's surface is constantly changing. Those mantle convection currents create the forces that move the tectonic plates, those large sections of the lithosphere.
Right.
It's the pulling, pushing, and sliding of these plates that causes earthquakes, builds mountains, creates volcanoes, and shapes continents and ocean basins over millions and millions of years.
So this fundamental layering and the continuous internal movement are literally the engine driving almost everything we see on the surface, from mountains to ocean trenches. It's why it matters to understand this basic structure. It's the foundation for everything else in geology.
Precisely.
Okay, so once the Earth cooled enough to form solid rock, what did that look like? This takes us into the study of rocks, or petrology. The sources tell us the word comes from the Greek petros, meaning rocks, and logos, meaning study. What does studying rocks really involve? More than just picking them up, I assume.
Yes, a bit more. It's about understanding their entire story, where they came from, what they're made of, how their mineral grains fit together, the texture, and the conditions under which they formed. It's really like detective work, figuring out the Earth's past environments and processes based on the rocks we find today.
And the sources classify rocks into three main families based on how they form. What are those?
Right, we have igneous rocks, which form from molten rock, magma, or lava. Then sedimentary rocks, formed from deposited fragments or precipitated minerals. And finally, metamorphic rocks, which are formed when existing rocks are transformed by heat and pressure.
Let's start with the igneous rocks, born from fire, you could say. The sources say they form either deep inside the Earth from magma or on the surface from lava.
That's the key distinction. Plutonic rocks, like granite, cool slowly underground. This gives their minerals time to grow large enough to see easily. With the naked eye, we call that a pheneric texture.
Okay, big crystals.
Big crystals. Volcanic rocks, like basalt, cool quickly on the surface from lava. This results in tiny or even invisible mineral grains, an aphanitic texture. So the cooling rate is basically written right into the texture of the rock.
The sources also list some really cool-sounding structures found in volcanic rocks. Vesicular amygdaloidal.
Yeah, vesicular texture is where gas bubbles left little voids or holes in the rock as it cooled. Amygdaloidal texture is when those voids get filled in later with new minerals, often quartz or calcite.
Ah, okay.
Then you have things like ropey texture from flowing, cooling lava, and those incredible columnar joints, often hexagonal, formed when lava contracts as it cools, like mud cracking, but on a massive scale.
Wow.
The sources even mention examples right here in Maharashtra and India, like the hexagon columns at Naldurga Fort or Gilbert Hill in Mumbai. And pillow structures tell us the lava actually erupted underwater.
Amazing. Okay, moving on to sedimentary rocks, these seem to tell a story of surface processes like weather and water, right?
Exactly. They form through a whole sequence of events. First, existing rocks are broken down by weathering and erosion. Then the fragments are transported, usually by water, wind, or ice. They get deposited in layers, often in lakes or oceans. And finally, they're compacted by the weight of overlying sediment and cemented together by minerals precipitating from groundwater. It happens over millions of years.
A slow process.
Incredibly slow, accumulating layers like pages in a book.
And how are these sedimentary layers classified? Is it by size?
That's one way, yes, by the size of the grains. The sources mention Wentworth-scale rudaceous rocks or coarse, like conglomerates and breccias, made of gravel or pebbles. Arenaceous rocks are sandy, like sandstone. Argillaceous rocks are fine-grained, like siltstone and shale, made of mud or clay. You can also classify them by how they form. Some are residual, like bauxite or laterite, which form in place when most minerals weather away, leaving behind the really insoluble stuff. Others are transported, like the sandstones and shales we just mentioned, and some form from biological activity, like coal or certain limestones, or by chemical precipitation from water, like rock salt.
And sedimentary rocks also contain structures that give clues about the ancient environment, like cross-bedding or ripple marks. What did those tell us?
Cross-bedding is fascinating. You see these angled layers within a larger horizontal layer. They actually indicate the direction of ancient currents, either water or wind, that deposited the sediment.
So you can tell which way the wind was blowing millions of years ago.
Pretty much, yeah. And ripple marks are basically fossilized waves or currents preserved on the bedding surface, telling us if water or wind was moving across the sediment surface, like footprints of the past environment.
Okay, finally, the metamorphic rocks, rocks that have changed form. What makes a rock transform like that?
It's all about putting existing rocks, could be igneous, sedimentary, or even other metamorphic rocks, under intense heat and pressure, usually deep within the earth. Often, hot fluids circulating through the rock play a role too. The original minerals become unstable under these new conditions, and they recrystallize or rearrange themselves to adapt. The sources define metamorphism quite nicely as the response of solid rocks to pronounced changes in their environment.
And the type of transformation depends on what's doing the work, right? Like whether it's mostly heat or mostly pressure.
Precisely. If directed pressure squeezing from a particular direction is dominant, you might see rocks mechanically crushed or developing a parallel alignment of minerals, like slaty cleavage. That's how shale can turn into slate.
Okay.
If heat is the dominant factor, maybe near a magma chamber, you get thermal or contact metamorphism, where the rock basically gets baked and recrystallizes.
And if it's both?
Often, it is both heat and directed pressure working together, especially during mountain building. That's called dynamo-thermal metamorphism. This can cause minerals to flatten out or even separate into distinct bands. This is how shale can progressively turn into phyllite, then schist, and finally gneiss, which often shows those characteristic light and dark bands.
So these changes create new structures in the metamorphic rocks.
Yes, distinctive structures. Slaty cleavage allows a rock to split into thin sheets. Schistosity is where platy minerals like mica are strongly aligned, giving the rock a sparkly look. Gneissos banding is that separation of minerals into distinct light and dark layers. These structures are clues about the intensity and direction of the pressure and heat the rock experienced.
So understanding these three main rock types isn't just about naming them, it's about understanding the fundamental materials Earth is made of and the immense ongoing processes melting, breaking down, compacting, transforming that shape them over billions of years.
Exactly. They tell the story of the planet.
Now, those rock layers we just talked about aren't just building blocks, they're also archives holding the story of Earth's past. That's where paleontology and stratigraphy come in. What exactly is paleontology?
Paleontology is the study of ancient life, primarily through fossils. The term comes from Greek roots, meaning ancient life study. Pretty straightforward. The sources clarify the modern definition. We're looking for recognizable structures in sedimentary rocks left by organisms that lived more than about 11,000 years ago, basically predating modern human civilization's major impact.
It seems kind of remarkable that anything from millions or even billions of years ago survives long enough to become a fossil. The odds must be low.
Oh, they are incredibly low.
Yeah.
The sources mention an estimate that maybe only 1 in 10,000 individual organisms actually becomes a fossil.
Wow.
For it to happen, you generally need a few key things. Quick burial is crucial. It protects the organism from decay, from scavengers, from being broken up. Usually this happens in sediment on a seabed or lake bed. Having hard parts helps immensely for bones, shells, teeth, wood. Soft parts rarely fossilize. And the material needs to be somewhat resistant to dissolution over time.
But when conditions are just right, the sources describe some incredible ways life can be preserved, not just bones and shells.
Not just bones and shells, no. You can get entire organisms preserved under exceptional circumstances. Think of woolly mammoths found frozen in ice in Siberia, or insects perfectly trapped in amber, which is fossilized tree resin.
Right, like in Jurassic Park.
Exactly like that. More commonly, you find preserved skeletons or shells. Petrification is amazing, too. That's where the original organic material is slowly replaced, literally molecule by minerals like silica or calcite dissolved in groundwater. It creates a perfect stone replica, like the petrified wood found in various places in India that the sources mention.
There are also simpler forms of preservation, right? Like casts and molds.
Yeah, those are like geological imprints. A mold is the hollow space left after an organism decays, and a cast is formed if that mold later gets filled with sediment or minerals. Carbonization is another way, where pressure squeezes out liquids and gases, leaving just a thin film of carbon, often preserving the outline of plants or delicate animals like graptolites.
And trace fossils, what are those?
Trace fossils are really interesting because they aren't the organism's body itself, but evidence of its activity. Things like fossilized footprints, tracks, trails, burrows dug into sediment, or even coprolites, fossilized dung.
Fossilized dung, okay.
It tells you about the animal's diet, so trace fossils tell us about behavior, not just what the organism looked like.
So beyond just being cool things to find in rocks, what do these fossils actually do for geologists? What are their main uses?
Fossils are incredibly valuable tools. The primary use, highlighted clearly in the sources, is determining the relative age of the rock layers they are found in. Because life has evolved over time, different organisms live during specific periods. Finding a specific type of fossil, especially an index fossil.
What's an index fossil?
An index fossil is one that's really useful for dating. It needs to be easily recognizable, geographically widespread, have lived for a relatively short period of geological time, and be quite common. Think of things like trilobites or ammonites. If you find one, you know roughly when that rock was formed.
Okay.
Fossils also provide critical information about ancient environments, paleoenvironments, with this area a shallow tropical sea, a deep ocean floor, a swamp, a desert. The types of fossils found in marine shells versus land plants, for instance, give us vital clues about the conditions when the rock was being deposited.
And speaking of using fossils to date and correlate rocks across different areas, that's where stratigraphy comes in, isn't it?
Exactly. Stratigraphy is the study of layered rocks, or strata. Its main goal is to arrange these rock units in chronological order to reconstruct Earth's history. If paleontology provides the dated markers, the fossils, stratigraphy provides the framework, the sequence of events.
And this field is built on some fundamental principles, some basic rules.
Yes, absolutely. One of the cornerstones is the principle of uniformitarianism, often summarized by the phrase, "The present is the key to the past."
What does that mean exactly?
It means that the geological process we see happening today, things like erosion by rivers, deposition of sand on beaches, volcanic eruptions, earthquakes causing faults, operated in essentially the same way throughout Earth's history. So if we see ripple marks forming on a modern beach from wave action,
Right.
we can infer that similar ripple marks we find preserved in ancient sandstone layers were formed by similar wave action millions of years ago. It allows us to interpret the past based on present observations.
Okay, that makes sense. Then there's the principle of superposition.
That one's pretty intuitive, but really powerful. It just states that in an undisturbed sequence of sedimentary rock layers, the oldest layers at the bottom and the youngest layers at the top, like stacking books, the first one you put down is at the bottom.
Simple enough. And the real game changer, according to the sources, was the principle of faunal succession.
Yes, this was a huge breakthrough, largely developed by William Smith, an English surveyor. He realized that fossil assemblages, the specific groups of different fossils found together in a rock layer, occur in a definite and determinable order through geological time. Life has evolved, so the collection of species alive at any one time is unique to that time.
So you can tell where you are in the timeline by the fossils.
Exactly. This ordered succession means we can correlate rock layers from different places, even across continents, just by finding the same characteristic fossil assemblage, even if the rock types themselves look different. It was the key that allowed geologists to start building a globally consistent geological timescale long before radiometric dating existed.
And these principles, combined later with techniques like radiometric dating for getting absolute ages for very old rocks, are how the standard geological timescale was developed, dividing Earth's 4.6 billion year history into eons, eras, periods, and epochs.
That's precisely how it was built, piece by piece, layer by layer, fossil by fossil. And lithostratigraphy is part of this too, organizing rock units based purely on their physical rock characteristics of their lithology. Geologists define mappable units like formations and groups based on rock type, regardless of age initially.
The sources even give us a brief outline of the stratigraphy of peninsular India, essentially a timeline of rock layers specific to this region. It's like a local history book.
It is. It's like reading the regional diary chapter by chapter. It starts way back with the very ancient Darwar supergroup from the Archean Eon, some of the oldest rocks in India, known for valuable iron, manganese, and gold deposits.
Sure.
Interestingly, these very old rocks typically lack clear evidence of early life. Moving forward in time, you get the Kadapa and Vindian supergroups from the Proterozoic Eon. These show different types of sediments accumulating, including limestones and sandstones, which are important sources for things like building stones, cement, and even diamonds in some areas. And in the Vindian rocks, we start to see hints of the earliest primitive life forms.
And then there's the Gondwana supergroup. That sounds important.
Crucial for India. These rocks were deposited from the Permo-Carboniferous period through to the Jurassic. They're famous for containing India's major coal deposits, the primary energy source for the country. They also hold rich plant and animal fossils, including evidence that links India to the ancient southern supercontinent, Gondwana.
Ah, hence the name.
Exactly. And finally, covering vast areas of central and western India, you have the Deccan basalts. Enormous volcanic lava flows erupted around the end of the Cretaceous period into the Eocene. These create the distinctive plateau landscape and features like columnar joints and amygdaloidal basalts we talked about earlier. Sometimes, between the flows, you find layers of sediment with freshwater fossils.
So, rocks and fossils aren't just dusty museum pieces. They are literal pages in Earth's billions of years old diary. They let us read back and understand its long, complex history, and even the specific history of regions like peninsular India.
Couldn't have said it better myself.
All that history is embedded in layers, but those layers aren't always flat and neat, are they? The immense forces inside Earth deform the rocks, which leads us to structural geology. The sources tell us features like folds, faults, and joints are the physical evidence of tectonic forces, stress and strain acting on the rocks.
That's right. Stress is the force applied per unit area on a rock, and strain is the resulting deformation, the change in shape or size of the rock in response to that stress. Think of squeezing or stretching clay. The sources distinguish between confining pressure, which is like the uniform pressure from the weight of overlying rocks squeezing equally from all sides deep underground, and directional stress, which is unequal pressure usually associated with tectonic plate interactions. This directional stress can be tensional, pulling apart, compressional, squeezing together, or shearing, sliding past.
And how the rock responds depends on the conditions.
Exactly. It depends on the type and amount of stress, the temperature, the confining pressure, the rock type itself, and how quickly the stress is applied. Under low temperature and pressure near the surface, rocks tend to behave in a brittle way. They fracture or break. Deeper down, where it's hotter and pressure is higher, rocks are more likely to deform in a ductile way. They bend or flow without breaking.
Like folding. But first, geologists need a way to describe the orientation of these rock layers and structures in 3D space, right? That's where strike and dip come in.
Correct. Strike and dip are fundamental measurements that define the attitude or orientation of an inclined rock layer or a fault plane. Strike is the compass direction of a horizontal line on that inclined surface. Imagine the water line on a tilted boat in the water that's the strike line.
Okay.
Dip is composed of two parts. The dip angle, which is the maximum angle that surface slopes downwards relative to the horizontal, and the dip direction, which is the compass direction in which it slopes downwards, always perpendicular to the strike. If you pour water on that tilted boat deck, the direction it flows is the dip direction, and the steepness is the dip angle. Geologists measure this using a special compass combined with a clinometer.
Got it. Okay, so one of the most visible results of compressional stress, especially ductile deformation, is folding.
Folds are bends or curves in originally flat rock layers, like wrinkling a rug by pushing the ends together. The sources describe the key parts of a fold, like the hinge line, the line of maximum curvature along the fold crest or trough, and the limbs, the sides or flanks of the fold on either side of the hinge.
And we can have different types of folds, depending on how they arch.
Yes. The simplest types are anticlines, which are upward arching folds, like an A shape, where the rock layers dip away from the central hinge line. In an eroded anticline, the oldest rocks are exposed in the core. Synclines are the opposite downward sagging folds, like a U shape or a trough, where the layers dip towards the central hinge line and the youngest rocks are found in the core.
And they can be symmetrical or asymmetrical.
Right. Symmetrical folds have an axial plane, an imaginary plane dividing the fold as symmetrically as possible, that is vertical, and the limbs dip at roughly equal angles but in opposite directions. Asymmetrical folds have an inclined axial plane, and the limbs dip at different angles.
Okay, so that's bending. But if the rock breaks instead, especially under brittle conditions due to stress, you get a fault.
Exactly. Faults are fractures in rocks where there has been significant movement or displacement of the rocks on either side of the fracture. They are evidence of brittle failure.
What are the main types of faults?
The sources describe several key types based on the relative movement. Normal faults are caused by tensional stress, pulling apart. The block of rock above the inclined fault plane, the hanging wall, moves down relative to the block below, the footwall.
Okay, tension pulls things apart and down?
Right. Reverse faults are caused by compressional stress, squeezing. Here, the hanging wall moves up relative to the footwall. Thrust faults are basically low-angle reverse faults, where the fault plane is tilted at less than 45 degrees, allowing blocks to be pushed over each other for large distances.
And movement can be sideways, too.
Yes, strike-slip faults involve horizontal movement, where the blocks slide sideways past each other, parallel to the strike of the fault. The San Andreas Fault in California is a famous example. The sources also mention related features like step faults, a series of parallel normal faults dropping the crust down in steps, and Horst and Greven structures.
Horst and Greven.
Yeah, these form where you have blocks of crust bounded by faults. A horst is an uplifted block between two normal faults, forming block mountains. A graben is a downdrop block, forming rift valleys. The East African Rift Valley is a classic example of graben formation.
Faults sound inherently bad, especially given their link to earthquakes. Are there any upsides?
Well, they can certainly be hazardous. The sources clearly mention they can create unstable ground for mining or engineering projects, act as pathways for landslides, and of course, they are the source zones for most earthquakes. But they aren't all bad from a resource perspective. Fault zones can act as important conduits for hot, mineral-rich fluids circulating through the crust. This can lead to the deposition of valuable metallic ores like gold, silver, or copper along the fault.
Interesting. Now, what if there's a fracture, but there hasn't been much movement along it? Is that different from a fault?
Yes, that's called a joint. Joints are fractures or cracks in rocks where there has been little to no discernible movement parallel to the fracture surface. They are extremely common and often occur in sets, with parallel joints creating patterns in the rock. A really distinctive type mentioned in the sources is columnar jointing.
Ah, we talked about those in volcanic rocks.
Exactly. Formed by the contraction of cooling lava flows, often resulting in those fantastic six-sided polygonal columns we see at places like Gilbert Hill or Neldurga Fort.
Okay. And the sources also bring up unconformities again. We touched on them with stratigraphy, but structurally, what are they?
Structurally, unconformities are major buried erosional surfaces. They represent significant gaps in the geological record at a particular location, where deposition stopped for a considerable time and erosion likely occurred before deposition resumed. They are essentially contacts between rock units where a chunk of geological time is missing. They represent buried landscapes.
And how do we recognize different types of unconformities in the field?
There are three main types described. An angular unconformity is often the most dramatic and easy to spot. You see older rock layers below the unconformity that have been tilted or folded and then eroded flat, before younger, horizontal layers were deposited on top. It clearly shows a period of deformation and erosion occurred between the two sequences.
Okay, that's clear. What about the others?
A disconformity occurs between parallel layers of sedimentary rock. The layers above and below the unconformity are parallel, but the surface between them is an irregular erosional surface, indicating a period of non-deposition and erosion without tilting. These can be harder to spot, sometimes identified by missing fossil zones or evidence of weathering on the surface. A nonconformity is where sedimentary rocks directly overlay older igneous or metamorphic rocks. This indicates that the deeper crystalline rocks were uplifted, eroded, and then subsided for sediments to be deposited on top.
And these unconformities aren't just academic curiosities, right? They have practical significance.
Definitely not just academic. The sources list several important aspects. They represent significant gaps in time, obviously. They help geologists subdivide complex stratigraphic sequences. They indicate past periods of tectonic activity, uplift, and erosion. They can influence groundwater flow and sometimes form traps for oil and natural gas. They can also be zones where certain types of mineral deposit, like uranium, accumulate. And, importantly for engineering, they can represent zones of weakness in the rock mass.
So these folds, faults, joints, and unconformities, they are the physical scars and structures left by the immense ongoing forces shaping our planet. Understanding them is crucial because they influence where we find resources, where it's safe or unsafe to build, and where natural hazards like earthquakes might occur.
Precisely. They tell a story of the forces at work.
Speaking of resources, let's shift gears and talk about the valuable materials geology helps us find and use Earth's wealth. This falls under economic geology.
Right. Economic geology is the branch that studies minerals and rocks that are economically important. It covers everything from understanding how these deposits form to exploration methods for finding them and considerations for their extraction and use. The sources really highlight how essential these geological resources are for modern industrial society and economic development. We depend on them for almost everything.
The sources list different categories of economic minerals. What are the broad groups?
They categorize them broadly into metallic minerals, things like iron, copper, aluminum, manganese, lead, zinc, gold, silver, which are valued for the metals they contain. Then, nonmetallic minerals, a huge group including things like limestone for cement, sand and gravel for construction, clays for ceramics, salt, phosphate for fertilizers, mica, quartz, feldspar, the list goes on. And finally, energy resources, primarily the fossil fuels like coal, petroleum, oil, and natural gas, but also includes uranium for nuclear power.
And India seems to have significant deposits of many of these based on the sources.
Yes, India is quite rich in several key resources. Iron ores, like hematite and magnetite, are abundant and fundamental for the steel industry, which underpins so much construction and manufacturing. Manganese ores are also significant, especially in states like Maharashtra and Madhya Pradesh, and are crucial for making steel alloys.
What about copper and aluminium?
India has notable copper deposits, essential for electrical wiring, plumbing, and alloys like brass and bronze. And bauxite, the main ore of aluminium, is found extensively, often as a residual deposit formed by intense weathering in tropical climates. Aluminium's lightweight and corrosion resistance make it incredibly useful.
And the energy resources are obviously critical for India's economy.
Absolutely critical. Coal, formed from ancient compressed plant matter over millions of years, is a major source of energy in India, particularly the coal found in the Gondwana rock sequences across the peninsula. The sources mention different types: anthracite, bituminous, lignite, peat, varying in quality and energy content.
And
Petroleum, or crude oil, is also vital. Geologically, it's not technically a mineral, as it's organic and liquid, but it's a crucial energy resource. It's a complex mixture of hydrocarbons formed from the remains of ancient marine organisms, trapped underground in porous rock layers. It has to be refined to produce useful products like petrol, diesel, kerosene, and asphalt.
Beyond mining-specific ores or fuels, rocks and minerals themselves are used directly in countless industries. Construction seems like a big one.
Huge. We use massive quantities of dimension stone, like granite or marble for buildings and monuments, and even more crushed rock, sand, and gravel as aggregate for making concrete and roads. The sources even mention the increasing use of industrial byproducts like fly ash from coal power plants and slag from steelmaking as additives in cement and concrete, which is good for sustainability.
What about industries needing really hard materials?
That's the abrasive industry. They rely on very hard minerals for cutting, grinding, and polishing other materials. Diamond is the hardest, of course, but others like corundum, ruby and sapphire are gem varieties, garnet, and even quartz are widely used. The sources note quartz gets its name from a word meaning hard and is used in abrasives, but also crucially in glassmaking, ceramics, and electronics because of its properties.
And the ceramic industry itself relies on specific minerals.
Yes, primarily clays like kaolin, which is essential for pottery, tiles, and porcelain. Feldspar is another key ingredient used as a flux to lower the melting temperature in ceramics and glass production. The sources mention different types like orthoclase and plagioclase feldspar. Modern ceramics are incredibly versatile, even used in high-tech applications like catalytic converters in cars to reduce pollution, or the heat-resistant tiles in the NASA Space Shuttle, an amazing example mentioned. They're often lighter and more resistant than metals.
And the refractory industry, what does that involve?
Refractories are materials designed to withstand extremely high temperatures, over 1,500 degrees Celsius, without melting or degrading. They're essential for lining furnaces, kilns, and reactors used in industries like steelmaking, cement production, and glass manufacturing. Minerals like fireclay, kyanite, bauxite, chromite, and graphite are used, depending on the specific chemical environment, acidic, basic, or neutral, and temperature requirements. Kyanite, for instance, transforms into mullite at high temperatures, which is very refractory.
It's also surprising to see minerals mentioned in the context of medicine.
Yes, the sources note the traditional use of certain minerals and metals in Ayurvedic medicine in India, a practice known as Rasa Shastra. Mica is given as an interesting example. Industrially, it's valued as an electrical insulator and filler, but the sources mention traditional Ayurvedic uses for preparing medicines purported to help with various ailments like anemia or asthma. Of course, the efficacy and safety of such traditional uses require careful scientific evaluation.
And the location of all these industries that use minerals isn't random, is it?
No, not usually. The sources point out several factors. Proximity to the raw materials is often key to reduce transport costs. Access to markets for the finished products is important. Availability of skilled labor, suitable land, energy, water, and transport infrastructure all play a role in deciding where to locate mines, processing plants, and factories.
So the ground beneath us isn't just passive rock and dirt. It's a fundamental pantry of resources that are absolutely essential to almost every part of modern life. From the structures we live and work in, to the energy that powers our world, to the materials used in countless manufactured goods and even some traditional practices.
Really underpins everything.
Many of those resources are solid, but another vital resource beneath our feet is water. That brings us to hydrogeology, the study of groundwater. This seems incredibly important.
It is absolutely critical, especially today, as freshwater becomes a more stressed resource globally due to population growth and climate change. Hydrogeology deals with how water occurs, moves, and is stored underground. The sources describe the basic vertical distribution of groundwater. Near the surface, you have the unsaturated zone, or zone of aeration, where the pore spaces in the soil and rock contain both water and air. Below that is the saturated zone, where all the pore spaces are completely filled with water.
And the boundary between them is the water table.
Exactly. The water table is the upper level of the saturated zone. Its depth can vary depending on rainfall, topography, and geology.
And where is that water actually stored underground? Just in empty spaces?
Essentially, yes. It's stored in the void spaces within the rocks and sediments. These can be intergranular spaces, the gaps between the individual grains of sand or gravel, which can vary hugely in size depending on the material. Water is also held in very tiny capillary spaces by surface tension, sometimes too tightly for it to flow easily.
Okay, so not all rocks hold or transmit water equally. There must be key properties involved.
Two absolutely key properties determine how good a rock is at holding and transmitting water: porosity and permeability. Porosity is the measure of the total void space in a rock, usually expressed as a percentage of the total volume. It tells you how much water the rock could potentially hold.
But holding it isn't enough, right? It needs to be able to flow.
Precisely. That's permeability. Permeability is the ability of the rock or soil to transmit fluids through its interconnected pore spaces. A rock can be highly porous, like clay having lots of tiny spaces, but if those spaces aren't well connected, it has very low permeability and water can't flow through it easily. Good aquifers, those rock units that can store and transmit usable quantities of water to wells, need both good porosity and good permeability. Think sandstones, conglomerates, fractured limestones, or certain fractured volcanic rocks.
The sources describe different types of aquifers based on how they're layered or confined.
Yes. An unconfined aquifer is the simplest type. It has an impermeable layer beneath it, but its upper surface is the water table, which is open to the atmosphere and can rise and fall with recharge. A perched aquifer is a special, localized case. It's a small body of groundwater held up by a lens of impermeable material, like clay, within the unsaturated zone, sitting above the main regional water table.
And confined aquifers.
Confined aquifers are sandwiched between two relatively impermeable layers, often called aquitards or aquicludes, like layers of shale or clay. The water within a confined aquifer is under pressure. Sometimes enough pressure that if you drill a well into it, the water will rise above the top of the aquifer without pumping. That's an artesian condition. The sources suggest using the term confined aquifer is often more accurate than artesian aquifer, though. There are also leaky aquifers, where the confining layers are not perfectly impermeable and allow some water to leak in or out.
Given how vital groundwater is, especially in places like India, conservation methods are crucial. The sources detail various approaches to rainwater harvesting.
Rainwater harvesting is becoming increasingly important. It's basically about collecting and storing precipitation locally, either for direct use or, more often, for recharging the groundwater aquifers. You can do rooftop harvesting, collecting the water that falls on your roof.
How do you recharge with that?
The sources describe several methods. Simple recharge pits can be dug near the building, filled with gravel and sand, allowing the roof water directed into them to slowly soak into the ground. Recharge trenches are similar, but longer, perhaps better for larger roof areas. You can even direct roof water into existing tube wells or dug wells, usually after passing it through a filter to remove debris. It's important, the sources note, to have a system to filter out leaves and dirt, and often to divert the first flush of rain after a dry spell, as it might wash contaminants off the roof.
And surface runoff, water flowing over the ground, can also be captured.
Yes, there are various techniques for surface rainwater harvesting, especially in rural or semi-urban areas. Simple structures like gully plugs, small barriers made of stones or soil built across small gullies, can slow down runoff, reduce soil erosion, and allow more water to infiltrate. Contour bunds are earthen banks built along the contours of slopes to achieve a similar effect.
What about larger structures?
Check dams are small dams built across streams to impound water temporarily, increasing recharge upstream. Gabion structures are wire mesh boxes filled with rocks, used similarly to check dams, but allowing some water flow through. Percolation tanks are specifically designed shallow reservoirs built across streams, often with an earthen dam, designed to hold runoff and allow it to percolate down through permeable strata below, directly recharging the aquifer. And dug well recharge involves channeling surface runoff directly into existing open wells, again usually with filtering.
The sources mention using a runoff coefficient. What's that for?
The runoff coefficient is basically an estimate of what fraction of the total rainfall on a given surface, like a roof or a paved area or a field, will actually become runoff, rather than soaking in or evaporating immediately. It depends on the surface type. A paved area has a much higher runoff coefficient than a forest floor. Knowing this coefficient helps you estimate how much water you could potentially harvest from a given catchment area.
And on a personal level, they talk about household water audits. That sounds useful.
It's a great idea. It's basically about systematically assessing how much water you use in your home for showering, flushing, washing, watering the garden, and identifying ways to reduce consumption through simple measures like fixing leaks, installing water-efficient fixtures, or changing habits. The sources suggest this can increase awareness and potentially cut household water usage by 20–40%, which collectively makes a big difference in protecting local water supplies and aquifers.
So, hydrogeology isn't just an academic field, it's fundamental to managing our most vital natural resource.
Absolutely. It's essential for supplying water for domestic use, industry, and agriculture. Understanding groundwater flow and storage allows us to design effective water supply systems, manage abstraction sustainably, and design structures for artificial recharge like those rainwater harvesting techniques. The sources really emphasize the importance of integrated water conservation and watershed management, linking it directly to sustaining the productivity of the land for food, fuel, and other needs. And they highlight how combining modern tech like remote sensing and GIS with local community knowledge and participation, as seen in successful initiatives in Maharashtra, is key to developing effective and sustainable water management strategies.
Water is life, and understanding how it moves and is stored underground and implementing sustainable practices like rainwater harvesting is crucial for everyone, right down to actions you can take in your own home or community.
Couldn't agree more.
All these internal dynamics and surface processes can sometimes express themselves in powerful and, frankly, dangerous ways, leading us to geohazards. What exactly are geohazards?
Geohazards are basically natural geological processes or phenomena that occur on Earth that pose risks to human life, property, infrastructure, and the environment. They're often dynamic and sometimes unstable expressions of Earth's internal energy and plate tectonic interactions. Earthquakes are perhaps the most widely known example.
Earthquakes, the sudden shaking of the ground. The sources mention over 1 million happen globally each year.
That's the estimate, yes. Most are too small to be felt, but thousands are strong enough to cause damage, and unfortunately, major ones cause significant loss of life and widespread destruction. The study of earthquakes and the seismic waves they generate is called seismology.
And these seismic waves, they're not all the same.
No, there are different types. First, you have body waves, which travel through the Earth's interior from the focus, the point where the earthquake rupture starts. There are two main types of body waves. Key waves, or primary waves, are the fastest. They're compressional waves, meaning they push and pull the rock in the direction the wave is traveling, like a sound wave. They can travel through solids, liquids, and gases.
Okay, fastest and compressional.
Then you have S waves, or secondary waves. They are slower than P waves and are shear waves. They move the rock particles perpendicular sideways to the direction the wave is traveling. Crucially, S waves can only travel through solid materials. They can't pass through liquids like the Earth's outer core. The time difference between the arrival of the P wave and the S wave at a seismic station is key. It tells you how far away the earthquake occurred.
And the waves that cause the most damage are often the surface waves, right?
Generally, yes. Surface waves travel along the Earth's surface, radiating outwards from the epicenter, the point on the surface directly above the focus. They arrive after the body waves and tend to have larger amplitudes and longer durations, which means more intense and prolonged shaking. There are two main types: love waves, which cause side-to-side horizontal shaking, and Rayleigh waves, which cause a rolling up and down motion, much like waves on the ocean. This complex shaking is typically responsible for the most destruction to buildings and infrastructure.
And geologists locate the earthquake's origin, the epicenter, by using data from multiple seismic stations.
Exactly. Because P waves travel faster than S waves, the time gap between their arrivals increases with distance from the earthquake. By measuring this SP time interval at least 3 different seismic stations, scientists can calculate the distance from each station to the epicenter. Then, using triangulation drawing circles on a map with radii equal to those calculated distances centered on each station. The point where the 3 circles intersect marks the epicenter.
Earthquakes are measured in terms of their intensity and magnitude. What's the difference?
Intensity scales, like the Modified Mercalli Intensity, MMI scale, described in the sources, measure the effects of the earthquake at a specific location. It's based on observations, what people felt, how much damage occurred to buildings of different types, were objects thrown around, did the ground crack. It describes the severity of shaking at that place. Magnitude scales, like the Richter scale, or more commonly used scales like moment magnitude today, measure the energy released at the earthquake's source, the focus. It's a single numerical value that represents the intrinsic size or strength of the earthquake, regardless of where you measure it.
And major earthquakes aren't random. They happen in specific zones or belts around the world.
That's right, because most earthquakes are directly related to movements along tectonic plate boundaries. The sources list the major earthquake belts. The Circum-Pacific Belt, often called the Ring of Fire, which encircles the Pacific Ocean. The Alpine Himalayan Belt, stretching from the Mediterranean region eastward through the Himalayas and Southeast Asia. This includes India. And the Mid-Oceanic Ridge System, running along the underwater mountain ranges where plates are pulling apart.
The effects of earthquakes can be devastating, going beyond just shaking buildings down.
Absolutely. Beyond the immediate collapse of structures, the sources mention significant secondary hazards. Fires are a major risk, often caused by broken gas lines or electrical wires, as tragically seen in past earthquakes like San Francisco in 1906 and Kobe, Japan in 1995. This highlights the need for earthquake-resistant building design and infrastructure. Earthquakes can also trigger devastating landslides, especially in mountainous areas. They can cause ground liquefaction, where water-saturated soil temporarily loses strength and behaves like a liquid. They can change river courses, cause floods, and disrupt groundwater levels. And crucially, large earthquakes occurring under the ocean floor can displace huge volumes of water, generating destructive tsunamis that can travel across entire oceans.
Can we predict when the next big one will hit? That's the million-dollar question.
It really is. And the sources are quite clear. Despite significant scientific advances in understanding earthquake processes and monitoring, precise prediction of the exact time, location, and magnitude of a major earthquake remains unreliable. It's currently not possible in a way that would allow for specific short-term warnings or evacuations.
But scientists do monitor for potential precursors.
Yes, they do extensive monitoring, looking for possible warning signs. The sources list several potential precursors that are studied, such as changes in the pattern of small earthquakes, seismicity, variations in the ratio of P-wave to S-wave velocities, subtle changes in ground elevation or tilt, changes in electrical resistivity of rocks, fluctuations in groundwater levels or radon gas emissions from wells, and even anecdotal reports of unusual animal behavior, although the latter is very difficult to verify scientifically. None of these have proven consistently reliable for short-term prediction, however.
So if prediction is unreliable, the focus must be on mitigation, preparing for the inevitable.
Exactly. Mitigation is key. This involves several strategies. Long-term seismic hazard assessment and monitoring to understand where earthquakes are most likely and how strong the shaking could be, developing early warning systems, which can provide seconds to perhaps a minute of warning after an earthquake starts, but before strong shaking arrives, implementing smart land use planning to avoid building critical facilities on active faults or unstable ground, enforcing strict earthquake-resistant building codes for new construction and retrofitting older buildings, educating the public about earthquake risks and safety measures, and ensuring critical infrastructure like dams, bridges, and pipelines are designed and built to withstand expected levels of shaking.
Okay, another significant geohazard mentioned is landslides. What causes those?
Landslides are basically the downslope movement of rock, debris, or earth under the influence of gravity. They can range from very slow creep to incredibly rapid rockfalls or debris flows. They're often complex, involving a mix of sliding and flowing material. Many factors contribute to slope instability. The type of soil or rock is important. Some materials are inherently weaker than others. The steepness of the slope is obviously critical. Water content plays a huge role. Water adds weight to the slope, and high pore water pressure can reduce the friction holding the material in place, effectively lubricating the slide.
What else can trigger them?
Other contributing factors include the presence of weak geological layers, joints, or faults dipping in the same direction as the slope, removal of vegetation, whose roots head bind soil, vibrations from earthquakes or even heavy traffic, volcanic activity, and human activities like undercutting slopes for roads or buildings, loading slopes with waste material, or changing drainage patterns.
How can we manage or prevent landslides, especially in vulnerable areas?
It starts with identifying high-risk areas through geological mapping, analyzing aerial photos, and conducting slope stability assessments. Prevention techniques often focus on managing water, improving surface drainage to divert water away from unstable slopes, and installing subsurface drainage to reduce poor water pressure. Sometimes unstable material can be removed from the top of a slope, or the slope angle can be reduced, benching or terracing. Building retaining walls at the base of slopes can provide support. In some cases, techniques like installing rock bolts, piles, or wire mesh netting are used to physically hold unstable rock or soil masses in place.
Finally, let's talk about volcanism, another dramatic expression of Earth's internal heat reaching the surface.
Volcanism encompasses all the processes related to the eruption of molten rock, magma, onto the Earth's surface as lava, along with associated gases and fragmented rock, pyroclastics. The type of volcano that forms depends heavily on the properties of the magma, particularly its viscosity, resistance to flow, and gas content.
The sources mention different types, like shield volcanoes.
Yes, shield volcanoes, like the ones that form the Hawaiian Islands, are typically the largest type of volcano in terms of volume. They have broad, gentle slopes built up over time by successive eruptions of very fluid, low-viscosity basaltic lava that can flow for long distances. Their eruptions are generally non-explosive, characterized by lava fountains and flows.
What about the classic cone-shaped ones?
Those are typically composite volcanoes, also called stratovolcanoes, like Mount Fuji in Japan or Mount Etna in Italy. They have steeper, conical shapes built from alternating layers of more viscous lava flows that don't travel as far, and layers of explosively erupted pyroclastic material, ash, cinders, bombs. Because their magma is thicker and often contains more gas, their eruptions can be much more explosive and dangerous. Volcanic domes are smaller features formed by very thick, highly viscous magma, often rhyolitic, that piles up around the vent. These can also be prone to collapse or explosive eruptions.
And volcanoes create a whole range of hazards, not just lava flows burning things.
That's right. While lava flows are certainly destructive to property, covering and burning everything in their path, they usually move slowly enough for people to evacuate. Often, the greater dangers come from other volcanic phenomena. Ash falls can be widespread, collapsing roofs under their weight, disrupting agriculture and transportation, especially aviation, and causing respiratory problems. Pyroclastic flows are perhaps the most deadly hazard. They are fast-moving, superheated avalanches of gas, ash, and rock fragments that race down the volcano's slopes, incinerating everything.
What else?
Lahars are destructive volcanic mud flows or debris flows, formed when volcanic ash and debris mix with water, from melting snow and ice, crater lakes, or heavy rain. They can travel long distances down river valleys, burying communities. Volcanic gases released during eruptions, like sulfur dioxide, carbon dioxide, can be toxic or cause acid rain. Large eruptions can also trigger floods if they block rivers, or tsunamis if they occur near or under the sea.
Is volcanic activity easier to predict than earthquakes? You mentioned monitoring earlier.
Generally, yes. Prediction of volcanic eruptions is often more successful than earthquake prediction, sometimes possible with warnings days, weeks, or even months in advance, although predicting the exact timing and style of eruption is still challenging. Scientists continuously monitor active volcanoes for precursors.
What kind of precursors?
These include subtle changes in the volcano's shape or ground surface elevation, swelling as magma moves upwards, measured precisely using GPS and tilt meters, increased seismic activities, small earthquakes and tremors generated by moving magma beneath volcano, changes in the amount or composition of gases being released from volcanic vents, changes in ground temperature or the temperature of hot springs, sometimes changes in local electrical or magnetic fields. Based on monitoring these signs, scientists can issue forecasts, general statements about likelihood, and sometimes more specific predictions.
And can we do anything to mitigate volcanic hazards besides evacuating?
Mitigation primarily involves thorough monitoring, creating detailed volcanic hazard maps that show the areas likely to be affected by different types of hazards, lava flows, pyroclastic flows, lahars, ashfall, and extensive public education and emergency planning in communities near active volcanoes. Direct intervention to control eruptions is very limited and usually only attempted in specific circumstances for lava flows, like building barriers or trying to cool flows with water, as was done in Iceland, or potentially draining crater lakes to reduce lahar risk. The main strategy is avoiding the hazardous zones and being prepared to evacuate when warnings are issued.
Geohazards are definitely a powerful and sometimes terrifying reminder of the Earth's immense restless energy. Understanding the processes behind earthquakes, landslides, and volcanoes, and the science of monitoring and mitigation is absolutely crucial for protecting ourselves and building safer, more resilient communities, especially in geologically active areas around the world.
It's about learning to live with a dynamic planet.
To study all these complex, dynamic Earth systems, especially on a large scale, geologists increasingly rely on modern technology. This brings us to our final area, remote sensing and GIS, basically, seeing the unseen. What is remote sensing?
Remote sensing, at its core, is the science and art of acquiring information about the Earth's surface or other objects without actually being in direct physical contact with it. It's about seeing from a distance. It's been around longer than satellites. Actually, the sources mention early experiments using cameras on hot air balloons back in the 1850s.
Wow, really?
Yeah. But civilian satellite-based remote sensing really took off in the early 1970s with NASA's Landsat program, initially called ERTS. Landsat has provided the longest continuous space-based record of Earth's land surface. Since then, many countries have launched Earth observation satellites. India has been a significant player with its successful IRS, Indian Remote Sensing series of satellites, starting in 1988, providing valuable data for resource management. And now there are advanced radar satellites like RISAT-1 too. The sources even credit Dr. Pasharity as the father of remote sensing in India, mentioning an early experiment using aerial photos to detect coconut tree disease.
So how does this seeing from afar actually work? What's the process?
Well, the basic process involves several steps. First, you need a source of energy, usually the sun for most Earth observation, that's the illumination. This energy travels through the atmosphere. It then interacts with the target feature on the ground. Different materials like water, vegetation, soil, rocks reflect and absorb this energy differently, creating a unique spectral signature. The reflected or emitted energy then travels back up through the atmosphere to a sensor mounted on a satellite or aircraft.
And the sensor records it.
The sensor records the energy, usually in different wavelength bands. This recorded data is then transmitted to a ground station, processed into digital images, and finally interpreted by analysts to extract useful information about the features on the ground.
You mentioned the sun as the energy source. That sounds like a passive system. Are there active systems too?
Yes, that's an important distinction. Passive remote sensing systems, like most optical cameras or sensors that record visible and infrared light, rely on naturally available energy, primarily reflected sunlight. This means they generally can't collect useful data at night, and clouds can obscure the view. Active remote sensing systems, on the other hand, provide their own source of energy. Radar, radio detection and ranging, and LiDAR, light detection and ranging, are common examples. They emit pulses of energy, radio waves or laser light, towards the target and measure the energy that is scattered back. Because they provide their own illumination, active systems can operate day or night, and radar waves can often penetrate clouds, making them very useful in many situations.
Okay, so once you have the satellite imagery, how do geologists or other scientists actually make sense of the patterns and features they see? It's not just a pretty picture, right?
No, interpretation is key. Geologists use several visual interpretation elements, listed in the sources, to identify and understand features in the imagery. Shape and size are basic clues, the distinct shape of an airport runway, a river meander or volcanic cone, or the relative size of settlements or reservoirs. Pattern refers to the spatial arrangement of objects. Think of the branching pattern of a river network, drainage pattern, the repetitive pattern of folded mountains, or the grid pattern of agricultural fields.
What about tone and texture?
Tone or color is fundamental. It refers to the relative brightness or color of objects in the image. Different features reflect differently in various wavelengths, so variations in tone or color help distinguish soil types. Vegetation health. Vegetation often appears bright red in standard false color infrared images. Water bodies, usually dark, rock types, etc. Texture refers to the frequency of tonal variations within an area, a smooth texture like calm water versus a coarse texture like a forest canopy or a rough texture like a rugged mountainous area. Association is also important, recognizing features based on other features commonly found with them, like sand dunes typically occurring in deserts or specific types of buildings indicating an urban area.
And the quality or usefulness of that image depends on its resolution. The sources mention several types.
Yes, resolution is crucial and has different aspects. Spatial resolution refers to the size of the smallest object that can be distinguished in the image, often defined by the pixel size on the ground. Higher spatial resolution, for example 1 meter, means you can see smaller details than lower resolution, for example 30 meters. Spectral resolution refers to the number and width of the specific wavelength bands. The sensor can record more bands, allow for finer discrimination between different materials. Radiometric resolution is the sensor's sensitivity to subtle differences in brightness or energy levels. Higher radiometric resolution allows detection of finer variations. And temporal resolution is how frequently the satellite revisits the same area. High temporal resolution, example daily revisit, is vital for monitoring dynamic phenomena like floods, vegetation growth, or disaster impacts.
Okay, so remote sensing gives us the images, the raw data from above, but then there's GIS, Geographic Information System. What does GIS add to this? How does it work with remote sensing?
GIS is a powerful computer-based system designed to capture, store, query, analyze, manage, and display all forms of geographically referenced information. Think of it as a smart map combined with a database. It takes spatial data, the location information like where things are, often derived from maps, GPS, or remote sensing imagery, and links it explicitly to attribute data descriptive information about what is at that location, like the type of rock, the depth of a well, the population of a town, the owner of a property.
How does it organize this data?
The core concept of GIS is organizing geographic data into thematic layers. You might have separate layers for geology, rivers, roads, elevation, land use, soil types, administrative boundaries, etc. Each layer contains features, points, lines, or polygons representing real-world objects, and these features are linked to tables containing their attribute information. GIS allows you to overlay and integrate these different layers for complex analysis.
The sources mentioned GIS can answer the 6 wise questions. What are those?
Yeah, that's a nice way to put it. It highlights the analytical power of GIS. By linking location where with characteristics what, who, and time when, GIS can help answer questions like, where is a particular feature located? What exists at a specific location? When did a change occur? Who is affected by a certain condition? Why do certain patterns exist? By analyzing relationships between layers. And how have things changed over time? It allows you to query and analyze the spatial relationships between different data sets in ways that would be incredibly difficult or impossible otherwise.
And the types of queries listed in the sources really show this analytical power in action.
Exactly. You can perform simple location queries. What's here? Where is X? You can do measurements. What's the distance between A and B? What's the area of this forest? Neighborhood analysis is powerful. What's adjacent to this park? What's within 2 kilometers of this well? Is this pipeline connected to the network?
Yeah.
You can query based on attributes. Find all properties with high soil quality. Who owns them? You can look for patterns in relationships. Does copper mineralization often occur near faults? Is there a relationship between elevation and vegetation type? And crucially, trend analysis. How did the city limits change between 1990 and 2020? What areas have experienced deforestation?
Remote sensing providing the data and GIS providing the analytical framework together, they seem incredibly powerful tools for studying the Earth and managing resources. What are some key applications?
They are essential across a huge range of applications mentioned in the sources. Disaster management and mitigation is a major one. They're used for mapping hazard zones before disaster strikes, like floodplains or landslide-prone areas. Assessing the extent of damage after an event, like mapping earthquake damage or flood inundation. Integrating real-time data from sensors or social media for early warning systems. And optimizing rescue and relief efforts by combining hazard maps with population data.
What about finding resources?
Yes, natural resources exploration heavily relies on RS and GIS. Identifying geological structures favorable for oil and gas accumulation, mapping mineral potential zones based on rock types and alteration patterns seen in satellite imagery. Increasingly important is planning for renewable energy, finding suitable locations for wind farms or solar power plants by analyzing data on wind speeds, solar radiance, slope, land cover, and proximity to transmission lines, all integrated within a GIS. The sources mention specific data sets used for this.
And they're vital for water management, too, which we discussed earlier.
Absolutely critical for water resources. Satellites monitor surface water extent, snow cover, and even provide indirect clues about groundwater changes by monitoring vegetation health or soil moisture. GIS is used to model surface water runoff and groundwater flow, identify potential sites for rainwater harvesting structures, delineate watershed boundaries, and integrate various data sets, terrain, climate, land use, geology, to fine-tune water conservation and management practices. The sources specifically highlight the importance of integrating this technology with GPS field data and local community input for effective watershed management, citing examples of organizations doing this work in Maharashtra. And GIS-based visualizations are powerful tools for educating stakeholders and building awareness about water issues.
It seems this ability to perform spatial analysis and create powerful visualizations is becoming almost ubiquitous now.
It really is. The sources point out its wide applicability, even mentioning its use in managing global events like the COVID-19 pandemic, where integrating health data, population data, movement data, and facility locations spatially was key for understanding spread and planning response. It's become such a fundamental tool that the sources emphasize that studying GIS is now essential for students in earth sciences and many related environmental and planning fields.
These technologies truly let us see the Earth in entirely new ways, understand incredibly complex, interconnected systems, and ultimately make more informed decisions about everything from managing precious resources sustainably to responding effectively to major disasters. Its geology brought powerfully into the digital age.
A vital toolkit for the 21st century.
Wow, that was quite the journey, wasn't it? Really digging deep into the Earth's internal structure, tracing its immense history through rocks and fossils, understanding the incredible forces that sculpt the surface.
Yeah, the folding.
Exploring the unbelievable wealth of resources hidden beneath our feet, learning about the hidden world of groundwater, which is so critical.
Absolutely.
Grappling with those powerful geohazards, and finally seeing how this amazing technology lets us study it all from afar.
Indeed. It's really remarkable when you step back and see how interconnected all these different aspects of geology actually are. From the planet's formation billions of years ago, right through to the critical resources and the hazards that impact us directly today.
And it all started from source material like this geology textbook we reviewed. It's kind of amazing what you can learn when you take the time to deep dive into these fundamental concepts.
It really is. And understanding these basics like how different rock types form or why groundwater moves the way it does or what those faults and folds actually represent in terms of Earth's forces, it's crucial. Not just for aspiring geologists, but really for any informed citizen living on this incredibly dynamic planet.
Exactly. So hopefully you've now got a shortcut, a better handle on being well informed about the dynamic planet right beneath your feet and all the processes that are constantly shaping it.
Which actually raises an important question for you, the listener, to consider. Thinking about all the structural features we discussed, those faults, the folds, the unconformities, those hidden complexities beneath the surface, how might a better understanding of these features influence critical decisions about where we choose to build major infrastructure, like dams or highways, or perhaps how we plan for the future growth of our cities in a particular region?
That's definitely something to think about. We hope you enjoyed this deep dive.